In this video, we're going to look at the quotient rule, and we're going to start with the proof of the quotient rule, even though the proof is not an expectation that you're responsible for. Okay, so we have a function right here defined as y is equal to f at x over g at x. We replace f at x with u, g at x with v, and we get this for y. We're going to multiply both sides by v, and that will have us with vy is equal to u. Now that we have vy is equal to u, we can differentiate both sides using the product rule. So recall that it is v times the derivative of y plus y times the derivative of v, and that is all with respect to x. I'm going to take this term right here, I'm going to highlight it, I'm moving it over to the other side so it becomes negative, and then I did multiply both sides by 1 over v to get rid of this v right here, and I'm left with this equation right here. The whole point is that I am trying to isolate for dy dx, because that right there is the derivative of two functions that are being divided by each other, as we see up here. Okay, so instead of y right here, I'm going to substitute u over v. So I'm going to write dy dx is equal to du dx, and then instead of y, I'm writing u over v dv dx. Sorry guys, that should look like more like a u du, right? And there we go right there, and then that's times 1 over v. I'm going to distribute that 1 over v, okay? By distributing the 1 over v, I should end up with dy dx is equal to 1 over v du dx minus u over v squared dv dx. Okay, we need to have a common denominator here, so I'm going to take this term, the second term right here, and I'm going to just move this to the side, and I'm going to multiply this by v over v, and then I end up with this right here, which is v du dx minus u dv dx, all over the common denominator now of v squared. Right there. Okay. If I back substitute u and v, then I will get dy dx, and instead of v, I'm going to write g at x. Okay, g at x was my denominator function, times the derivative of my numerator function, minus the numerator function, which was f at x, that was u, times the derivative of the denominator function. Derivative, sorry, dg at x, dx. All of that is all over the denominator function, now all squared. And we can see that rule right here. Just one correction that needs to be made. This should be a minus right there. Okay. So we have the denominator function times the derivative of the numerator function minus the numerator function times the derivative of the denominator function, all over the denominator function squared. That is the quotient rule. Let's put that into use right now. Okay, we're going to differentiate this and determine the slope of the tangent at x is equal to 1. Okay, so this right here, this x squared plus 3x is my numerator function. The x cubed plus 1 is my denominator function. So again, I'm going to say that this right here, I do to find the derivative, I take the denominator function and I multiply that by the derivative of the numerator function. Sorry, 2x plus 3, right there. And then I subtract that with the numerator function times the derivative of the denominator function, which should just be 3x. All of that will be over the denominator function squared. At this point, I don't need to really clean things up that much because I'm given a value at x is equal to 1, right? So now I can just say, all right, well, f prime at 1, so wherever I see an x, I'm going to replace that with a 1. So 1 cubed plus 1 times 2 times 1 plus 3 minus 1 squared plus 3 times 1 times 3 times 1 all over 1 cubed plus 1 all squared, and I get f at 1, or f prime at 1, is equal to negative 1/2. And what that does, again, that means that is the slope of the tangent at x is equal to 1. Okay, on the next example right here. Okay, so in this next example here, we have a rational function, and my rational function is y is equal to x minus 1 all over x squared. And so this is asking me to differentiate this function. So I'm going to differentiate this function by using the quotient formula as or the quotient rule as we just learned. So we take the denominator function times the derivative of the numerator function, and the derivative of the numerator function should just be 1. Then we subtract and we do the derivative of the denominator function, which is 2x, times the, sorry, I'll color code that. That should be 2x times the numerator function, which is x minus 1, all over the denominator function squared. Okay. Yeah, so let's clean this up a little bit, and we get x squared minus 2x squared plus 2x, all over x to the power 4. Okay, cleaning this up further, y prime is equal to 2x minus x squared all over x to the power 4. Okay, so this will give me the slope of the tangent at any value of x. The only thing that you need to note is that x cannot be equal to 0. There is a vertical asymptote at x is equal to 0. It is not part of the domain. Okay, so it says find the points where the tangent is horizontal. Well, if this is the slope of the tangent and I have a horizontal tangent, then that means that the slope of the tangent would be 0. So right there, the slope would be equal to 0. So the first derivative is equal to 0. 0 is equal to 2x minus x squared all over x to the power of 4. Remember, a fraction can only equal to 0 if the numerator equals to 0. So therefore, 0 is equal to 2x minus x squared. 0 is equal to x, 2 minus x. And so that means that x could be equal to 0 or x could be equal to 2. We're not going to count x is equal to 0. That's not a possible answer because we know we have a vertical asymptote at x is equal to 0. So the only place where there could be a horizontal tangent is at 2. If I sub that back into my original equation, right, so I sub 2 into y is equal to x minus 1 all over x squared, then I can get the point where there is a horizontal tangent, and the horizontal tangent is at 2 1/4. Okay, it says graph the function as well, so we've got some steps here on how to graph a rational function. We can find any vertical asymptotes, so the first thing I'm going to do is vertical asymptotes. And my vertical asymptote is going to be at x is equal to 0. I've already established that by looking at the original equation. X can't be equal to 0. But because it is even, that means it's going to approach infinite. So it's going to approach either positive infinity or negative infinity symmetrically, which means like, you know, on the same side, right? Okay, so it's going to, we'll call it just same approach. Right, so it's going to approach it on both sides of the asymptote. Okay. All right, so that's my vertical asymptote, and so I've got, I'll put that in right there, at x is equal to 0, doing this rather quickly. Okay. Second is horizontal asymptote, right, for my end behavior. And if I look at this function right here, I can see that the numerator is going to grow much slower than the denominator, or you could say that the denominator is growing a lot faster than the numerator. So that means that as x goes to positive or negative infinity, as x gets really, really big, my denominator gets really, really big, which means that my whole number will go towards 0. Okay, so I've got a horizontal asymptote at y is equal to 0. Okay, 3, use a test point if necessary. Okay, so I'm just going to pick, we'll say x is equal to -4. x is equal to negative 4. If x is equal to negative 4, I'll put that into my equation. If x is equal to negative 4, y is equal to negative 4 minus 1 all over negative 4 squared. So therefore y is equal to negative 5 over 16. Okay, so I have a test point right here, negative 4 right here, which means therefore this function is going to go towards 0 from the bottom right there. Okay, so it's going to go towards 0 from the bottom. 4. Find the x-intercepts. Okay, so this function can only, so to find the x-intercepts, I set y is equal to 0. 0 is equal to x minus 1 over x squared. So again, a fraction can only equal to 0 if the numerator is equal to 0, so that means x is equal to 1. Okay, so 1, 0 is my x-intercept. I put that over here, and that's my only x-intercept. So this tells me right here that this function has to go down towards negative infinity. That's a horrible curve. Let me try that again. Okay, and then I know because it was an even degree asymptote, right? I'm going to come up and I'm going to go up this way right here, and then I'm going to come down. And note that I have like a peak right here, roughly, at 2 1/4. That's where my horizontal asymptote is. Sorry, not my horizontal asymptote, my horizontal tangent, right? That's where the slope is 0. This right here is 1, 0. That's the x-intercept. And note that I don't need to find any y-intercepts here because there's a vertical asymptote at x is equal to 0. All right, so that's the way this graph looks. Yeah, we were able to find the feature of this, one of the features of this, which is the absolute maximum of this graph, right, that turning point at 2 1/4 by setting the first derivative equal to 0. And I only got the first derivative by using the quotient rule. All right, so that's it. That's the lesson on the quotient rule. Hope you enjoyed it, and see you in the next one.